Nobel laureates in physics and chemistry, laureates in economic sciences, your excellencies, members of the Academy, ladies and gentlemen. On behalf of the Royal Swedish Academy of Sciences, I wish you all welcome to the 2024 Nobel Lectures in Physics and Chemistry and to the lectures of the Sveriges Riksbank Prize in Economic Sciences in memory of Alfred Nobel. The Nobel Prizes have been awarded since 1901 by the terms of the will of Alfred Nobel. Alfred Nobel was an inventor, a scientist and a businessman that in 1895 gave his fortune to 5 international prizes that corresponded to his interest and own activities. The Nobel Prize in Physics is awarded for discoveries and inventions, and in chemistry for discoveries and improvements that have conferred the greatest benefit to humankind. The Sveriges Riksbank Prize in Economic Sciences in memory of Alfred Nobel was instituted in 1968 at the tercentenary of the bank. And we are pleased to see you all here to listen to the Nobel Prize and Economy Prize lectures. Year 2024 has been a dramatic year with many crises ongoing at the same time. The geopolitical landscape has become more unstable, with several conflicts and military engagement. Fortunately, the inflation has gone down and the COVID-19 pandemic is over. But the energy crisis continues and we are facing an emerging climate change and a decreased biodiversity. And all these challenges underline the importance of enabling new discoveries, inventions, and improvement that will benefit humankind to get a better environment and health for all. And over the years, we have seen extraordinary technological advances that hopefully will help humankind in addressing these challenges. Since we don't know today what will be the challenges tomorrow, we need to use a broad bottom-up approach for new scientific discoveries. And these must be driven by curiosity and deep insights. Academic freedom is important, and top scientific discoveries cannot be ordered. And the way forward to discovery is usually not short and straight, but often long and winding. And surprises may pave the way for groundbreaking discoveries. We have now the privilege and honor to listen to exceptional researchers and laureates who have increased our knowledge fundamentally in 3 different areas of research. The laureates of this year's Nobel Prize in Physics have performed important work on artificial neural networks using tools from physics. And the laureates have developed methods that form the basis for machine learning. And machine learning and artificial neural networks have applications in many diverse fields, both in industry and academia. And it affects us all in many ways, from image and speech recognition to medical applications. In the Nobel Prize in Chemistry, the laureates have discovered a way to build entirely new kinds of proteins. And proteins are important building blocks in the body. Also, the laureates have developed a model based on artificial intelligence and machine learning to predict complex structures of proteins based on the primary amino acid sequence. And these discoveries hold enormous potential also for the future. The laureates in this year's prize in economic sciences have demonstrated the importance of societal institutions for differences in countries' prosperity. Inclusive institutions were often introduced in countries that were poor when they were colonized, which over time resulted in a prosperous population. And this is an important reason for why former colonies that once were rich are now poor and vice versa. And all these achievements not only bring new knowledge and deeper understanding, but also allow us to improve our societies in multiple ways and to take wiser decisions. And we will now listen to these prize lectures by these exceptional researchers on whose shoulders present and future humans can stand, and new giants in research will surely arise. So once more, most welcome and my warmest congratulations to the laureates. And I now invite my colleague in the Academy of Sciences, Professor Ellen Moons, Chair of the Nobel Committee for Physics, to introduce the laureates in physics.
Honored Nobel laureates, Your Excellencies, distinguished colleagues, dear students, ladies and gentlemen, a warm welcome to the 2024 Nobel Lectures in Physics. This year's Nobel Prize in Physics is about artificial neural networks and their central role in the revolutionary development of machine learning. Machine learning is the ability of a computer to learn from examples instead of following instructions of programmed recipes. Artificial neural networks are the foundational building block of machine learning. By feeding a neural network with large amounts of data, be it images, speech, or music, it is trained to recognize patterns. Once it has learned to find these patterns, it can generate new data that resemble the ones in the given data set. Giving it millions of pictures of cats, it will learn what a cat looks like and how it differs from a dog, without having to follow gradually narrowing programmed subroutines describing the taxonomy of mammals and the meowing and purring sounds that they make. I do not need to convince you that today this new technology has drastically changed our daily lives. Also in research areas as diverse as particle physics, protein crystallography, material science, astrophysics, artificial neural networks have contributed to discoveries and inventions of great importance. But how did it all start? How are artificial neural networks built, and how do they work? As long ago as the early 1980s, this year's Nobel laureates, John Hopfield and Geoffrey Hinton, made foundational discoveries and inventions that enable machine learning with artificial neural networks. Incurably curious about how our brain works, with the billions of neurons wired together by uncountable connections, they searched for answers to the questions of how we humans learn, how we process and categorize information, and how we recognize new information by association to the stored memories in the data sets, to the stored memories and experiences, John Hopfield made groundbreaking contributions by describing the dynamic model of associative memory using fundamental concepts from physics, the physics that describe collective phenomena. He used the same equations and models that govern the physics of magnetic materials to describe the interactions in the brain. Geoffrey Hinton applied concepts from statistical physics to develop efficient neural networks with multiple layers. He developed learning algorithms and methods for the networks to self-improve. It's now my pleasure and great honor to introduce our first speaker, John Hopfield. John Hopfield was born in Chicago, 1933. He received his first degree from Westmore College in 1954. He earned his PhD in 1958 from Cornell University. He was appointed professor of physics at Princeton University in 1964. And in 1980, he became professor of chemistry and biology at California Institute of Technology. He returned then to Princeton University, where he presently is affiliated as emeritus professor in molecular biology. Please join me in welcoming John Hopfield to the stage to tell us about the developments that led to this year's Nobel Prize of Physics.
Thank you for the introduction. Thank you, thank you. Thank you for coming. There we go. My first full-time employment was at the Bell Telephone Laboratories, where the transistor had been invented 10 years earlier. I joined its 6-person theoretical physics group in March 1958. A full half-day of employment was spent on administrative detail. I headed for my new office. Unpacking a few books and journals took an hour. A visit to the fifth floor stockroom produced some lined tablets, pencils, and a hand-cranked pencil sharpener. I returned to my office and sharpened several pencils. Now what should I do? That stark question has plagued me many times in my research and teaching career. Every scientist, every scholar faces this vexing issue of what to work on each day. Most respond by working today to extend a little yesterday's line of thought or line of measurement, or plot development. Most of us spend little time thinking seriously about choosing the research area we next pursue. You hear very few lectures on how to choose a research direction. Yet the choice of problem is the primary determinant of what one accomplishes in science. 2 papers that I wrote more than 40 years ago form the basis of the work often referred to as the Hopfield model. I will first describe how the subject developed, some of the choices made, the situations encountered, ultimately defining the germ of a useful viewpoint on which mathematics could be overlaid. For shorthand, I refer to this process as problem choice, but it really is a description of how a useful point of view was winnowed from an analysis of random events from my past. When viewed with historical hindsight, the development of a problem is often presented as a logical sequence of correct choices. In a branching decision tree. Without the benefit of hindsight, research is often pursued in random directions, taken with no overwhelming insight. To me, growing up with a father and mother, both of whom were physicists, physics was not defined by subject matter, the atom, the troposphere, a piece of glass, my bicycle, a magnet, the atom. These are all incidentally the subject matter. Physics was a point of view that the world around us, with effort, ingenuity, and adequate resources, is understandable in a predictive and reasonably quantitative fashion. Being a physicist is a dedication to a quest for this kind of understanding. Of course, neither of my parents ever spoke of what defines physics. It was only much later that I thought about how my upbringing had defined a useful worldview. I grew up taking things apart, seeing how they worked, repairing bicycles, exploring chemistry, building flyable model airplanes, crystal sets, and simple radios, playing with batteries, and learning to think with my hands and manipulate real objects. Each thing I understood, why my bicycle brakes got hot when they were used, how a consistent story could be incorporated as a small part of a much grander understanding in a complicated system. Heedless of the financial consequences of being a physicist, I only briefly considered it an alternative career. My high school chemistry teacher had been superb, while my physics teacher lacked an understanding even of the rudiments of electricity and magnetism. Thus influenced, when listing potential majors on college applications, I wrote physics or chemistry. At Swarthmore College, I was assigned Professor William Elmore as my advisor. We met in his office to discuss my future. He located the student card describing my high school record and thus the field of study I was interested in, took out a pen and crossed out 2 words, remarking, "I don't believe we need to consider chemistry." And that is the way my education went. An arbitrary act by Bill Elmore had much to do with my being here today. I began looking at graduate schools in physics with an eye to what I might specialize in. My upbringing had particularly focused my interest on the physics of the daily world and its technologies. I went to graduate school at Cornell because in 1954, Cornell had a segment of the physics department interested in a field called solid-state physics. In the middle of my second year at Cornell, I approached theoretical physicist Albert W. Overhauser to ask if he would supervise my thesis and help me find a thesis problem. Through courses and doing problem sets, I was rapidly acquiring the tools of theoretical physics, but I had no idea of how to find an appropriate research problem. Happily, Overhauser had a list of interesting puzzles. They were often in the form of a paradox. Elementary theoretical analysis of a particular phenomenon in solid-state physics gives result B. Root A over here is what experiments get, and they're totally different. In most paradoxes in this list, Overhauser himself had no idea of what was producing the conflict between a common-sense theoretical view and the experimental facts. I picked a problem having to do with the radiative lifetime of an exciton in a crystal. Overhauser was enormously supportive as a listener and a critic when I went to see him, but finding direction and resolving technical theoretical issues were entirely my problem. The great gift he gave me was the ownership of an interesting question and total responsibility for research and progress. I've done my best to repay my mentors my mentor Overhauser, through similarly nurturing another generation of independent students, a couple of which are actually here today. PhD in hand, I took a position in the theory group at Bell Laboratories. Conyers Herring was head of the group and saw me struggling to identify my next problem to work on. He suggested visiting with experimentalists to get my own sense of where interesting puzzles lay. This was the framework within which I met chemist David Thomas, and we formed a working theory-experiment alliance. It was to provide me with unanticipated problems and paradoxes for 10 years and provide AT&T with a major knowledge base in compound semiconductors. It garnered David and me a joint Oliver E. Buckley Solid-State Physics Prize from the American Physical Society in 1969. At the time, no one would have guessed that the combination of light and compound semiconductors would have a major technological role in the future. By 1968, I had run out of problems in condensed matter physics to which my particular talents seemed useful. I went to the Cavendish Laboratory of Cambridge University in the UK on a Guggenheim Fellowship for half a year, hoping to find new interesting avenues, but found little for me. Returning from Cambridge to Princeton University and my consultancy in the semiconductor group at Bell Labs, I ran into Robert J. Schulman, a chemist who was doing the first high-resolution nuclear magnetic experiments on hemoglobin. Bob told me about the cooperative oxygen binding at the 4 iron atoms in the center of the widely separated heme groups of the protein. An incredible panoply of physics techniques was being used to study the molecule: NMR, EPR, optical spectroscopy, neutron scattering, Mossbauer spectroscopy. All the clever experimental techniques of solid-state physics seemed relevant to understanding hemoglobin. Hemoglobin provided me a simple entree from condensed matter physics to biological matter physics. In both fields, the goal was to understand how structure and low-lying excitations were related to measurable and relevant properties. It seemed that my background in condensed matter physics might find good use in biology. When Linus Pauling, a double Nobelist in chemistry and in peace, was asked about choosing problems to work on, he remarked, "I ask myself whether the problem I am considering is one to which I am likely to make a contribution." I would clearly need to emulate Pauling. I had become interested in the unexpectedly small number of mistakes made in choosing the correct amino acid when the next amino acid is inserted in a protein during protein synthesis within a cell. How might I make my physics background more likely to see a solution to this problem? Free energy is the key. High-energy molecules like glucose or ATP are expensive for a cell to make, and a biochemical process using unexpectedly large numbers of high-energy molecules in a simple process must be paying dearly for that cost for a purpose. Suppose that the purpose was to proofread, to remove biosynthesis errors, Perhaps experimental biochemists had not noticed because they did not know how to look. I was successful in that problem. I found a plausible scheme for proofreading and protein synthesis based on known biochemical detail and described critical experiments to test the theory. I gave a talk at Harvard Medical School in 1976, ending with a brief account of proofreading and my prediction about non-stoichiometry in protein synthesis. The first question after my talk was Robert C. Thompson. He asked, "Would you like to hear the results of such an experimental measurement?" And went on to describe his experiments, not yet published, in my measuring the stoichiometry ratios when a system was being pushed to proofread and when it was not. He described experimental facts which just overwhelmingly pushed the idea proofreading works that way. It was one of the biggest and most delightful surprises of my brief career in chemistry. Now, let's see if I can get this right. Yes. This 1974 paper was important in my approach to biological problems, for it led me to think about the function of the structure of a reaction network, rather than just what is the function of the biological molecule. 6 years later, I was generalizing this view and thinking about networks of neurons rather than the properties of single nerve cells. Writing this paper, doing this research, also led me to think more about problem identification and biophysical research. The unexpected success of this paper was due to its formulation of a new biological problem and had nothing to do with my knowledge of biochemistry or biophysics. Chance had favored the unprepared, but the inquiring mind. I spent the winter of 1977 at the Bohr Institute in Copenhagen as part of its sporadic but historical outreach toward biology. My task was to run a broad Modern Biology for Physicists seminar series. In 1932, Niels Bohr had opened the International Congress on Light Therapy with a lecture entitled Light and Life. Bohr asked whether a deep explanation of life itself and the philosophical ambiguities of how to interpret quantum mechanics were intrinsically intertwined. However, in 1977, my distinguished experts in biology emphasized what they understood. They certainly did not describe biological science as being in need of help from physicists. I returned to Princeton without a new problem for myself. I was now looking for a big problem whose resolution and understanding will be of significance far beyond its normal disciplinary boundaries, and will reorganize the fields from which they came. Bold, prone to failure. My Princeton University office telephone rang shortly before my morning class, expecting a call about important things, tennis. I answered only to find Francis O. Schmidt on the line. He said he ran the neuroscience research program at MIT, would be transiting Princeton next Wednesday, and would greatly appreciate a half hour, no more, of my time. I had never heard either of the Schmidt or the NRP needed to head off That's what I'm supposed to avoid. Yes. For needed to head off for lecture, thought, what's 30 minutes, and agreed to meet. The following week, Francis O. Schmidt descended on me. He described his neuroscience research program, which chiefly held small meetings in Boston, attended by 20 regular members and 20 visitors. I told him I knew nothing of neuroscience. He said, that doesn't matter, just speak on what interests you. So I talked about my theory of kinetic proofreading and the general issue of accuracy in biosynthesis. The audience, neurologists, immunologists, electrophysiologists, neuroanatomists, understood little of what I said. It didn't matter. Frank wanted to add a physicist member to the group, hoping to bring someone with diverse science experience to interact with this subject and perhaps help it become more integrated and a more predictive science. I was captivated by the talks at the meeting. How mind emerges from brain is to me the deepest question posed by our humanity. It was being pursued in narrow slices as little problems by the NRP Club of Scientists with diverse talents and great enthusiasm. But it appeared to me that this group of scientists would never possibly be able to address the big problem, because the solution can be expressed only as an appropriate mathematical language and structure. None then involved with the NRP moved easily in this sphere, so I joined the group hoping to define, construct, or discover something I could usefully do in this field. My basic education in neurobiology came from attending the semi-annual NRP meetings, sitting next to world experts in their field who would patiently explain to me what the speaker was really trying to talk about. I tasked myself with finding an integrated physics view that's what I've done wrong. Yeah. Of trying somehow to rise above the disjoint details of lectures, neuroanatomy, electrophysiology, learning in the rat and Alzheimer's disease, and find some kind of integrated structure to theory. In 1979, Caltech appointed me to a professorship jointly between chemistry and biology, and I left Princeton. The quantum computing facility at Caltech was a splendid environment for trying out models. It supported multi-user real-time computing, video displays, direct keyboard input, all things you say are trivial, but in 1979 they were a marvelous thing to discover. My insight was that basic machine or brain operation computed by following a machine trajectory in state space from the beginning where you put the program and data started, and then every tick of the clock, the state of the system moved. Ultimately, the state stopped changing. When the state stopped changing, the computation must be done. You'd read out some of the registers, and the computation had actually been done by following in a dynamical trajectory from start to end. That trajectory needs stability against perturbations to reach a correct answer in spite of noise and system This picture of batch mode digital computation is just a schematic to try to, just try to get the impression of here's what Hopfield views as computation. I turn finally to a more specifically chosen question than just a general one, and trying to focus on something which an animal needs, or animals are known to have. And this turned into something which became fundamentally related to behaviors a psychologist might call associative memory, or an engineer might call content addressable memory, or another psychologist would describe this as declarative memory, something you can describe. And these names share a common feature. They share a common basic paradigm that can be described as computing by a dynamical system which follows a trajectory which is stable, and thus small perturbations away from that trajectory are squeezed back onto it, and that's the way you go from start to finish in a noisy system. That's what content addressable memory does in a very different regime. But all of these, a whole bunch of things associated, I can't get by without using that term. I'm exercising, of course, associative memory as I speak. But all these things require what is a mathematician would describe as convergent flows. Once I grasped that point, I had heard enough about the mathematics of spin systems as they are related to magnetism and complex phenomena in magnetic materials. I'd been at Bell Labs enough to be around when people were seriously talking about these subjects, and so I knew something about the connection between spin systems and trajectories. And I only had to say, let's make the biological system look like a spin system, and then they should have the same kind of mathematics. Associative memory is reciprocal. Seeing someone reminds you of remember their name, and hearing their name reminds you of what they look like. That fact can be expressed in a network structure by making connections that are reciprocal. The mathematics of such networks was closely related to the mathematics of spin systems as seen in solids and to things having to do with their phase transitions in magnetism. Suddenly there was a connection between neurobiology on the one hand and the solid-state physics I sort of knew on the other. One way to achieve a convergent flow is for a state to be associated with an energy and have the allowed transitions state to state to state allowed such transitions to take place only if the energy was decreasing. Like a ball rolling downhill on a rough terrain. If you want to understand the trajectory of the ball, you could follow the terrain and the ball in detail, or you can understand there's an energy. The whole thing is just going downhill, and you go from near the top of the hill to near the bottom of the hill. And the energy function is what you really need to understand convergent flows in a wide range of systems. With that connection made, 3 months later I was writing a paper. Everything really came together when I see these two parts of science are really being described by the same set of mathematics. So now the problem became of writing a paper. I had 3 target reader audiences for such research: physicists, computer scientists, and neurobiologists. Disparate set of people, but being a member of the National Academy of Science, I could publish a paper in PNAS, Proceedings at the National Academy, without review. But for PNAS, there was an absolute 5-paper limit on article length, including references, and there were these 3 different audiences to address and much to say. I had to write science in the style that Hemingway wrote nonfiction. In hindsight, the omission of the almost obvious increased the impact of the paper. The unstated became an invitation for others to add to the subject, and thus encouraged an expanding community of contributors to work on such network models. This 1982 paper is the first publication in which I used the word neuron. It was to provide an entryway to working in neuroscience for many physicists and computer scientists. Further work connected these networks to many significant applications far beyond associative memory, including the emerging field of artificial neural networks. It also brought many statistical physicists into the field and created a foundation for subsequent development of the Boltzmann machine. Continuous associative memory networks also served as inspiration for continuous recurrent networks frequently used in many contemporary AI systems and in complicated computational neuroscience. One issue with what is now called the Hopfield model network of associative memory is that it has a small information storage capacity. Biological networks can store many more memories than the number of sensory neurons and can dynamically adapt these memories if the environment changes. I was jolted into thinking about this problem in 2015 when I was a visiting professor at the Institute for Advanced Study in Princeton and was starting to interact with Dmitry Krotov, a former high-energy theorist who was searching for an interesting problem to work on. After several months of discussion, we formulated a simple mathematical model in which the memory capacity becomes decoupled from the dimensionality of the space. This new model allows for a denser packing of memories, and we called it the dense associative memory as a result. Looking forward, we hope that the idea of useful computation by physical systems will not only become helpful in hindsight for interpreting computational algorithms in existing AI architectures, it may also inspire a new generation of collective physics-inspired AI networks. What I have done in science rests on the experimental and theoretical studies of experts. I have great respect for experts willing to interact with those outside their disciplines, welcoming physics into new territory. Physics at its best is a point of view for understanding the totality of man and his universe. Thank you.
It is now my pleasure and great honor to introduce our second speaker, Geoffrey Hinton. Geoffrey Hinton was born in London, UK in 1947. He received a bachelor degree in experimental psychology from Cambridge University in 1970. 1978, he was awarded a PhD in artificial intelligence from the University of Edinburgh. After postdoctoral research, he worked for 5 years as a faculty member in computer science at Carnegie Mellon University in Pittsburgh. In 1987, he was appointed professor of computer science at the University of Toronto, Canada, where he presently is emeritus professor. Between 2013 and 2023, he shared his time between academic research and Google Brain. Please join me in welcoming Geoffrey Hinton to the stage to tell us about the developments that led to this year's Nobel Prize in Physics.
So today I'm going to do something very foolish. I'm going to try and describe a complicated technical idea for a general audience without using any equations. So first I have to explain Hopfield nets, and I'm going to explain the version with binary neurons that have states of 1 or 0. So on the right there you'll see a little Hopfield net, and the most important thing is the neurons have symmetrically weighted connections between them. The global state of a whole network is called a configuration, just so we seem a bit like physics. And each configuration has a goodness. And the goodness of configuration is simply the sum over all pairs of units of neurons that are both on, of the weights between them. So those weights in red boxes, you add those up, and you get 4, hopefully. That's the goodness of that configuration of the network. And the energy is just minus the goodness. So these networks will settle to energy minima. The whole point of a Hopfield net is that each neuron can locally compute what it needs to do in order to reduce the energy, where energy is badness. So, if the total weighted input coming from other active neurons is positive, the neuron should turn on. If the total weighted input coming from other active neurons is negative, it should turn off. And if each neuron just keeps using that rule, and we pick them at random and keep applying that rule, we will eventually settle to an energy minimum. So the configuration on the right there is actually an energy minimum. It has an energy of -4, and if you take any neuron there, the ones that are on want to stay on, they get total positive input. The ones that are off want to stay off, they get total negative input. But it's not the only energy minimum. A Hopfield net can have many energy minima, and where it ends up depends on where you start it, and also on the sequence of random decisions you make. The sequence of random decisions about which neuron to update. So that's a better energy minimum. Now we've turned on the triangle of units on the right, and that's got a goodness of 3 plus 3 minus 1 is 5, and so an energy of -5, that's a better minimum. Now, Hopfield proposed that a good way to use such networks is to make the energy minima correspond to memories. And then using that binary decision rule about whether you should turn a neuron on or off, that can clean up incomplete memories. So you start with a partial memory, and then you just keep applying this decision rule, and it will clean it up. So settling to energy minima, when they represent memories, is a way of having a content-addressable memory. You can access an item in the memory by just turning on some of the item, and then using this rule, and it'll fill it out. Terry Sinofsky and I, Terry was a student of Hopfield's, proposed a different use for these kinds of nets. Instead of using them to store memories, we could use them to construct interpretations of sensory input. So the idea is you have a net. It has both visible neurons and hidden neurons. The visible neurons are where you show it a sensory input, maybe a binary image. The hidden neurons are where it constructs the interpretation of that sensory input. And the energy of a configuration of the network represents the badness of the interpretation. So we want low energy interpretations. So I'm going to give you a concrete example. Consider that ambiguous line drawing at the top. People have two ways of seeing that. There's interpretation one, which is normally what you see first. There's another interpretation, and when you see it as a convex object, that's clearly a different 3D interpretation of the same 2D line drawing. So could we make one of these networks come up with two different interpretations of the same line drawing? Well, we need to start by thinking what a line in an image tells you about 3D edges. So that green line is the image plane. Imagine you're looking through a window and you're drawing the edges in the scene out there in the world on the window. So that little black line is a line in the image. And the two red lines are the lines of sight that come from your eye through the ends of that line. And if you ask, well, what edge in the world could have caused that? Well, there's many edges that could have caused it. There's one edge that could have caused that 2D line. But there's another one. And there's another one, and there's another one. All of these edges will cause the same line in the image. So the problem of vision is to go backwards from the single line in the image to figure out which of these edges is really out there. You can only see one of them at a time if objects are opaque, because they all get in each other's way. So you know that that line in the image has to depict one of these edges, but you don't know which one. We could build a network where we started off by turning the lines into activations of line neurons. So let's suppose we already have that. We have a large number of neurons to represent lines in the image, and we turn on just a few of them to represent the lines in this particular image. Now, each of those lines could depict a number of different 3D edges. So what we do is we connect that line neuron to a whole bunch of 3D edge neurons with excitatory connections, those are the green ones, but we know we can only see one of those at a time, so we make those edge neurons inhibit each other. So now we've captured a lot about the sort of optics of perception. We do that for all of our line neurons. And now the question is, which of those edge neurons should we turn on? For that we need more information, and there's certain principles we use in interpreting images. If you see two lines in an image, you assume that if they join in the image, they join in depth where they join. That is, they're at the same depth where the two lines join in the image. So we can put in extra connections for that. We could put in a connection between every pair of 3D edge neurons that join in depth at the point where they have the same end. We could put in a stronger connection if they join at right angles. We really like to see images in which things join at right angles. So we put in a whole bunch of connections like that. And now what we hope is, if we set the connection strengths right, that we've got a network which has two alternative states it can settle to, corresponding to those two alternative interpretations of the Necker cube. This gives rise to two main problems. The first problem, if we're going to use hidden neurons to come up with interpretations of images represented in the states of the visible neurons, is the search issue. How do we avoid getting trapped in local optima? We might settle to a rather poor interpretation and not be able to jump out of it to a better interpretation. And the second problem is learning. I sort of implied I'd put in all those connections by hand, but we'd like a neural network to put in all those connections. So, the search problem we solve, more or less, by making the neurons noisy. So if you have deterministic neurons, like in a standard Hopfield net, if the system settled into one energy minimum, like A, so the ball there is the state of the whole, is the configuration of the whole system, it can't get from A to B because the decision rule for the neurons only allows things to go downhill in energy. And the graph on the right is the decision rule. If the input's positive, turn on. If the input's negative, turn off. We would like to be able to get from A to B, but that means we have to go uphill in energy. And the solution to that is to have noisy neurons, stochastic binary neurons, They still only have binary states. Their states are either 1 or 0, but they're probabilistic. If they get a big positive input, they almost always turn on. With a big negative input, they almost always turn off. But if the input is soft, if it's somewhere near 0, then they behave probabilistically. If it's positive, they usually turn on, but occasionally turn off. And if it's a small negative input, they usually turn off, but occasionally turn on. But they don't have real values. They're always binary, but they make just these probabilistic decisions. And so now if we want to interpret a binary image using these hidden neurons, what we do is we clamp the binary image on the visible units. That specifies what the input is. And then we pick a hidden neuron at random. We look at the total input it's getting from the other active hidden neurons, and we start them all off in random states. And if it gets total positive input, we probably turn it on, but we might just turn it off if it's only a small positive input. So we keep implementing this rule of turn them on if they're big positive input, off if they're big negative input, but if they're soft, make probabilistic decisions. And if we go round and we keep picking hidden neurons and doing that, the system will eventually approach what's called thermal equilibrium. That's a difficult concept for non-physicists, and I'll explain it later. Once it's reached thermal equilibrium, the states of the hidden neurons are then an interpretation of that input. So in the case of that line drawing, the hidden neurons, you'd hopefully have one hidden neuron turned on for each line unit, and you get an interpretation which will be one of those two interpretations of the Necker cube. And what we hope is that the low energy interpretations will be good interpretations of the data. So for this line drawing, if we could learn the right weights between the 2D line neurons and the 3D edge neurons, and learn the right weights between the 3D edge neurons, then hopefully the low energy states of the network would correspond to good interpretations, namely seeing 3D rectangular objects. So thermal equilibrium. It's not what you first expect, which is that the system is settled to a stable state. What's stabilized is not the state of the system. What's stabilized is a far more abstract thing that's hard to think about. It's the probability distribution over configurations of the system. That's very hard for a normal person to think about. It settles to a particular distribution called the Boltzmann distribution. And in the Boltzmann distribution, the probability, once it's settled to thermal equilibrium, of finding the system in a particular configuration is determined solely by the energy of that configuration. And you have more probability of finding it in lower energy configurations. So at thermal equilibrium, the good states, the low energy states, are more probable than the bad states. Now, to think about thermal equilibrium, there's a trick physicists use, and it allows ordinary people to understand this concept, hopefully. You just imagine a very large ensemble, gazillions of them, of identical networks. You have these gazillion Hopfield networks. They all have exactly the same weights. So they're the same system, essentially. But you start them all off in different random states, and they all make their own independent random decisions. And there'll be a certain fraction of the systems that have each configuration. And to begin with, that fraction will just depend on how you started them off. Maybe you start them off randomly, so all configurations are equally likely. And in this huge ensemble, you'll get equal numbers of systems in every possible configuration. But then you start running this algorithm of update neurons in such a way that they tend to lower the energy, but occasionally allow it to go up. And gradually what will happen is the fraction of the systems in any one configuration will stabilize. So any one system will be jumping between configurations, but the fraction of all the systems in a particular configuration will be stable. So one system may leave a configuration, but other systems will go into that configuration. This is called detailed balance, and the fraction of systems will stay stable. That's it for the physics. So let's imagine generating an image now. Not interpreting an image, but generating an image. To generate an image, you start by picking random states for all of the neurons, the hidden neurons and the visible neurons. Then you pick a hidden or visible neuron, and you update its state using the usual stochastic rule. If it's got lots of positive input, probably turn it on. Lots of negative input, probably turn it off. If it's soft, it behaves a bit stochastically. And you keep doing that. And if you keep doing that repeatedly until the systems approach thermal equilibrium, then you look at the states of the visible units, And that's now an image generated by this network from the distribution it believes in, the Boltzmann distribution, in which low energy configurations are much more likely than high energy configurations. But it believes in many possible alternative images, and you can pick one of them, one of the things it believes in, by running this process. Okay. So, now what's the aim of learning in a Boltzmann machine? The aim of learning in a Boltzmann machine is to make it so when the network's generating images, think of it as dreaming, it's just randomly imagining things. When it's generating images, those images look like the images it perceives when it's doing perception on real images. If we can achieve that, then the states of the hidden neurons will actually be a good way to interpret the real images. They'll capture the underlying causes of the image. At least that's the hope. Another way of saying that is, learning the weights in the network is equivalent to figuring out how to use those hidden neurons so that the network will generate images that look like the real images. That seems like an extremely hard problem. Everybody thought that's going to be very complicated. It turns out Terry and I had an outrageously optimistic approach. The question is, could you start with a neural net, a Hopfield net, of this stochastic kind of Hopfield net, that has lots of hidden neurons, and they just have random weights between them. And they have random weights connecting them to the visible neurons. So it's a big random neural net. And then you just show it lots of images. And we're hoping for something that seems ridiculous, which is that on perceiving lots of real images, it will create all the connections between the hidden units and between the hidden units and the visible units. It'll weight those connections correctly so that it comes up with sensible interpretations of images in terms of causes like 3D edges that join at right angles. That sounds very optimistic. And you might have thought that the learning algorithm to do that would be very complicated. The amazing thing about Boltzmann machines is there's a very simple learning algorithm that will do that. This was discovered by Terry Sanofsky and me in 1983. And the learning algorithm goes like this. It has two phases. There's a wake phase. That's the phase when the network is being presented with images. You clamp an image on the visible units, you let the hidden units rattle around and settle down to thermal equilibrium, and then, once the hidden units are at thermal equilibrium with the visible neurons, for every pair of connected neurons, either two hiddens or a visible and a hidden, if they're both on, you add a small amount to the weight between them. That's a pretty simple learning rule. That's a learning rule that people who believe in Donald Hebb would like. Then there's a sleep phase. Obviously, if you just run the wake phase, the weights will only get bigger, and pretty soon they'll all be positive, and all the neurons will turn on all the time. That's not much good. You need to combine it with a sleep phase. And in the sleep phase, you can think of the network as dreaming. You're settling to thermal equilibrium by updating the states of all the neurons, the hidden ones and the visible ones. And once you've done that and reached thermal equilibrium, for every pair of connected neurons, if they're both on, you subtract a small amount from the weight between them. That's a pretty simple learning algorithm. And it's pretty amazing that it does the right thing. So, on average, that learning algorithm changes the weights so as to increase the probability that the images the network generates when it's dreaming will look like the images it sees when it's perceiving. And not for the general audience, so you mustn't read this next two lines. For statisticians and machine learning people, what that algorithm is doing is, in expectation, that means it's doing it very noisily and often does the wrong thing, but on average, in expectation, it follows the gradient of the log likelihood. That is, in expectation, what it's doing is making it more likely that the network will generate when it's dreaming the kinds of images it sees when it's awake. Or to put it another way, the weights change so that the images the network finds plausible, low-energy images, resemble the images that it sees when it's awake. And what the learning is doing, of course, what's happening in that learning algorithm is in the wake, you're lowering the energy of the whole configurations of the network that it arrives at when it sees real data. And when it's asleep, you're raising the energy of those configurations. So what you're trying to make it do is believe in what you see when you're awake and unbelieve in what you dream when you're asleep. Okay. So if you ask what the process of settling to thermal equilibrium achieves, it achieves something amazing, which is that everything that one weight in the network needs to know about all the other weights. And to know how to change one weight, you need to know something about all the other weights. They all interact. But everything you need to know shows up in the difference between two correlations. It shows up in the difference between how often the two neurons are on together when the network's observing data, and how often they're on together when the network isn't observing data, when it's dreaming. And somehow, those correlations measured in those two situations tell a weight everything it needs to know about all the other weights. The reason that's surprising is because in an algorithm like backpropagation, which is what all the neural nets now actually use, you require a backward pass to convey information about the other weights. And that backward pass behaves very differently from the forward pass. In the forward pass, you're communicating activities of neurons to later layers of neurons. In the backward pass, you're conveying sensitivities. You're conveying a different kind of quantity altogether. And that makes backpropagation rather implausible as a theory of how the brain works. And so when Terry came up with this theory, this learning procedure for Boltzmann machines, we were completely convinced that must be how the brain works, and we decided we were going to get the Nobel Prize in physiology or medicine. It never occurred to us that if it wasn't how the brain works, we could get the Nobel Prize in physics. Okay, there's only one problem, and the problem is that settling to thermal equilibrium is a very slow process for very big networks with large weights. If the weights are very small, you can do it quickly. But when the weights are big, after it's learned some stuff, it's very slow. So actually, Boltzmann machines are a wonderful romantic idea. They're this beautifully simple learning algorithm, which is doing something very complicated. It's constructing these whole networks of hidden units that interpret the data by using a very simple algorithm. And the only thing is that they're just much too slow. So that was that for Boltzmann machines. And the lecture should really have ended there. But 17 years later, I realized that if you restrict Boltzmann machines a lot and just have hidden units that aren't connected to each other, then you can get a much faster learning algorithm. So if there's no connection between the hidden neurons, then the wake phase becomes very simple. What you do is you clamp an input on the visible units to represent an image, and then in parallel now, you can update all the hidden neurons, and you've now reached thermal equilibrium. You just update them all once. They just look at the visible input and randomly pick one of their two states based on how much input they're getting. And now you're at thermal equilibrium in one step. That's great. For the hidden neurons, you still have a problem. In the sleep phase, you have to put the network in some random state, update the hidden neurons, update the visible neurons, update the hidden neurons, update the visible neurons, and you have to go on a long time to reach thermal equilibrium. And so the algorithm is still hopeless. But it turns out there's a shortcut. The shortcut doesn't quite do the right thing, which is embarrassing, but it works pretty well in practice. So the shortcut works like this. You put data on the visible units. That's an image. And then you update all the hidden neurons in parallel. And they've now reached thermal equilibrium with the data. You now update all the visible units, and you get what we call a reconstruction. It's going to be like the data, but not quite the same. Now you update all the hidden units again. And then you stop. That's it. You're done. And the way you do learning is you measure how often the neurons I and J, the visible neuron I and the hidden neuron J, are on together when you're showing it data and it's reached equilibrium with data, and you measure how often they're on together when you're showing it reconstructions and it's reached equilibrium with the reconstruction, and that difference is your learning algorithm. You just change the weights in proportion to that difference. And that actually works pretty well, and it's much, much faster. It's fast enough to make Boltzmann machines finally practical. So, okay. So Netflix actually used restricted Boltzmann machines combined with other methods to decide which new movies to suggest you look at based on the preferences of all sorts of other users who are a bit like you. And they actually worked. They won the competition. This combination of Boltzmann machines and these other methods won the Netflix competition for how well can you predict what users will like. But of course, with just hidden neurons that aren't connected to each other, you can't build layers of feature detectors, which are what you need for recognizing objects in images or recognizing words in speech. And it looks like there's this strong restriction of having just one layer of hidden units without connections between them. But actually, you can get around that. So what you can do is you can stack these restricted Boltzmann machines. What you do is you take your data, you show the restricted Boltzmann machine, RBM, the data. It has just one hidden layer, and using this contrastive divergence algorithm that just goes up and down and up again, you learn some weights so that the hidden units capture structure in the data. The hidden units turn into feature detectors that capture commonly correlated things in the data. Then you take those hidden activity patterns, the binary activity patterns in the hidden units, and you treat those as data. So you just copy those into another RBM, and they're the data for the other RBM, and that second RBM looks at these features that have captured correlations in the data, and it captures correlations between those features. And you keep going like that, so you're capturing more and more complicated correlations. And so you can learn a second set of weights, W2. And you can do it as many times as you like. Let's learn a third set of weights. So now we've got a bunch of separate Boltzmann machines, each of which is finding structure among the hidden units of the previous Boltzmann machine. Then what you can do is you can stack up these Boltzmann machines and just treat them as a feed-forward net. So ignore the fact the connections are symmetrical. Just use the connections in one direction now, because you've got a way of getting, in your first hidden layer, you've extracted features that capture correlations in the raw data. And then in your second hidden layer, you've extracted features that capture correlations in the features extracted in the first hidden layer, and so on. So you're getting more and more abstract features, correlations among correlations. Once you've stacked them up like that, then you can just add a final hidden layer, like this, and you can do supervised learning. That is, now you can start telling it about the names of things, like cat and dog. Those are the class labels, and you're going to have to learn the weights to those class labels. But you start with this network that you've initialized by learning a stack of Boltzmann machines. And two beautiful things happen. The first beautiful thing is, if you initialize this way, the network learns much faster than if you initialize with random weights, because it's already learned a whole bunch of sensible features for modeling structure in the data. It hasn't learned anything about what things are called, but it's learned about the structure in the data. And then learning what things are called is relatively quick. Just like with small children, they don't have to be told, that's a cow, 2,000 times before they know that's a cow. They figure out the concept of cow for themselves, and then their mother says, that's a cow, and they've got it. Well, maybe twice. So it makes it much faster to learn, for example, to recognize objects in images. It also makes the networks generalize much better. Because they've done most of the learning without using labels, they don't need many labels now. They're not extracting all the information from the labels, they're extracting the information from the correlations in the data. And that makes them generalize much better with needing far fewer labels. So that was all very nice. And between about 2006 and 2011, people were using, particularly in my lab and Yoshua Benjo's lab and Jan's lab, people were using stacks of RBMs to pre-train feed-forward neural networks, and then they would apply backpropagation. And in 2009, two students in my lab, George Dahl and Abdul Rahman Mohammed, showed that this technique worked a little bit better than the best existing techniques for recognizing fragments of phonemes in speech. And that then changed the speech recognition community. My graduate students went off to the various leading speech groups, and in 2012, things based on exactly this, stacked up restricted Boltzmann machines, went into production at Google, and they got better speech recognition. Suddenly, the speech recognition on the Android got a lot better. Unfortunately for Boltzmann machines, once we'd shown that these deep neural networks really worked very well if you pre-trained them with stacks of restricted Boltzmann machines, people found other ways of initializing the weights, and they no longer use stacks of Boltzmann machines. But if you're a chemist, you know that enzymes are useful things. And even though RBMs are no longer used, they allowed us to make the transition from thinking that deep neural networks would never work to seeing that deep neural networks actually could be made to work rather easily if you initialize them this way. Once you've made the transition, you don't need the enzyme anymore. So think of them as historical enzymes. The idea of using unlearning during sleep, though, to get an algorithm that's more biologically plausible and avoids the backward path of backpropagation, I still think there's a lot of mileage in that idea, and I'm still optimistic that when we do eventually understand how the brain learns, it will turn out to involve using sleep to do unlearning. So I'm still optimistic, and I think I'm done.
Very nice. Thank you very much. So please join me now in welcoming both laureates on the stage to jointly receive our warmest applause. Maybe you would like to step forward and in front. Maybe you would like to go in front here.